Hello everyone, I would like to convey my thanks to the third International Conference in Geotechnical Engineering for giving me this opportunity to present my research on shear and degradation behavior of rail track ballast contaminated with fines and experimental study. I am Venuja. I am a research assistant at Department of Civil Engineering, University of Peradeniya. I will start my presentation with a brief background. Ballasted rail tracks are the most popular one all over the world due to the availability of low-cost raw material and simplicity of construction. It also involves low initial construction cost. Ballasted rail tracks has many components such as rails, fastener system, sleepers, ballast, subballast, and subgrade. These components can be categorized into two main categories such as superstructure and substructure. Ballast is a highly angular granular material which can be obtained from blasting rocks such as granite, quartzite, limestone, basalt, and dolomite. When we look at the rail track system, ballast layer is the major component by weight and volume. It effectively transmits the train exerted loads from sleepers to the underlying layers at a minimal level. And also it serves as a bed to rails and sleepers and provide overall track stability. With the time, the performance of ballast decreases with the repetitive train loads due to the lack of lateral confinement, ballast breakage, and ballast fouling. Ballast fouling is the phenomena where the voids in the ballast layer are partially or fully filled with the fine materials such as sand, coal, silt, dust, clay, and broken ballast particles. As you can see from the figure 3, with the time fouling is increasing. When the fouling is higher, the contact between the nearby particles are almost vanished. So ballast fouling is one of the major factor in ballast degradation. We can look at the consequences of ballast degradation. It affects the load bearing capacity and shear strength of the ballast layer. Therefore, it leads to differential settlements and misalignments of rails. It reduces the permeability and comfort and safety concerns are raised. Therefore, there is a necessity for regular monitoring and it involves high-cost maintenance activities. Therefore, this study analyzed the shear and breakage behavior of ballast with various fouling materials such as sand and clay. Let's look at the methodology of this research. Materials such as ballast, river sand, and clay were collected from Gampola Stockyard and Digane area respectively. Figure 6 shows the particle size distribution of ballast and river sand used in this study. Ballast sizes were obtained using the upper and lower limits adapted in Indian Railways. Figure 7 shows the photograph taken during the sieving of ballast. The table shows the test plan. 4 types of samples were tested, such as pressed ballast, ballast with 15% and 10% of sand fouling, and ballast with 5% of clay fouling. All 4 samples were tested under 3 different normal loads, such as 30, 60, and 90 kilopascal. This figure shows the large-scale direct shear test apparatus designed and constructed at Geotechnical Laboratory in the University of Peradeniya. It has 400 mm diameter and 150 mm height, 2 equal cylindrical halves, and normal load is applicable using a lever arm system. Vertical, horizontal dial gauges and load cell are used to extract the results, and hydraulic jack is used to give the shear rating to the sample. So initially ballast particles were sieved and washed thoroughly with clean water. After drying, the predetermined amount of ballast in each sieve interval was mixed and prepared sample into 3 layers. For fresh ballast test, each layer was placed and each layer was compacted using a rubber padded hammer. For the tests on sand fall ballast, the predetermined amount of sand poured on top of the ballast already placed into the apparatus, and a shutter vibrator was used to apply the vibration to the apparatus where the sand can be settled in the voids of the ballast sample. For the tests on clay fouled ballast, clay was coated for each layer before placing into the apparatus using wet mixing method. Normal stress was applied on the sample using a lever arm system as shown in the figure previously. A constant shearing rate of 4 mm per minute was applied until 60 mm shear displacement was attained. So, as I mentioned previously, horizontal and vertical displacement gauges and load cell were used to extract the results using a data logger system. Since the shear area is circular shaped, a correction factor suggested by Olson and Leib was used in the calculation. The graph shows the shear stress variation of all 4 types of samples under different normal loads with the shear strain. As you can see, when we take any kind of sample, there is an increase in shear stress with higher normal loads. This is due to the increase in frictional resistance that is caused by the higher particle interlocking. When we look at the peak shear stress of each samples, at normal stresses like 30 kilopascal, all the samples were showed lower shear stress compared to the fresh ballast. This is due to the lubricant behavior of the fouling agents. For sand fouling at higher normal loads, the shear stress is higher compared with the fresh ballast. This is due to the densification effect of sand fouling. But for the clay fouling, for all normal loads, it shows reduced shear stress. This is due to the loss of frictional behavior between particles due to the lubricant behavior of clay fouling. Table shows the friction angles of different samples. Then we'll move on to the breakage behavior of fresh and fouled ballast. Ballast breakage index was calculated using the method suggested by Navaratnarajah et al. In 2005. At higher normal stresses, there is a high BBI was obtained for all kind of sample. This is due to the reduced dilation, which increases the ballast particles breakage. With the fouling, in both cases, the BBI was reduced. This is because of the densification for sand fouling and lubricant behavior for clay fouling. And then I'll come to the conclusions of my research. So normal stresses, fouling material and fouling percentage have impacts on shear stress and breakage behavior of ballast. There is an increase in shear stress when the normal stress increases. For all samples, this is due to the high frictional resistance provided by the high particle interlocking. The intrusion of sand particles densify the sample. Therefore, there is an increase in shear stress at higher normal loads compared with the fresh ballast. When we compare the clay fouled sample, due to the lubricant behavior of clay fouling, there is a reduction in surface friction. Therefore, the overall shear stress of sample is reduced compared with the fresh ballast. Also, ballast breakage is higher at high normal loads and it reduces with the falling material intrusion. So I would like to convey my gratitude to AHEAD grant and University of Peradeniya research grant for funding this research, and thank you all for listening to me patiently.